Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, I'm going to describe optimization trials. We're going to go ahead and create an optimization trial and then talk about what's involved to get it set up and ready to run. All right, what I have on my screen here is a watershed that's already been set up and delineated, and it's ready for an optimization trial to be added to it. You can download the files for this project, and I'm going to leave a link in the description of this video. So you can click that link, scroll all the way down to the bottom, and then click on the zip icon to download the files if you want to play around with this particular model. Optimization is the process of finding an optimal or near optimal solution to a problem. In the context of hydrology and HEC HMS, optimization is used to modify parameter data so that the model output data most closely represents observed data from the real world. So the observed data is considered the perfect data or the target data that we want the model output to match. We're going to start by creating an optimization trial by going up to the Compute menu and then Optimization Trial Manager. Here we have a list box showing all the existing optimization trials. And then when we select that, we can click Copy, Rename, Edit, Delete, and View Messages. To create a new optimization trial, we'll just go ahead and click New here, and a dialog box pops up. It's the first of a three-step wizard we need to complete. Also, another way to bring up that box but quicker is just to go up to Compute, Create Compute, Optimization Trial. Here we go. Now, these options won't be available to you unless your project already contains a basin model and at least one meteorologic model. Right now, I have one basin model and four meteorologic models, which we'll be seeing in just a moment. So we're going to go Compute and then Optimization Trial. The first step is to create a name for the optimization trial. And where that name is going to show up is under the Compute tab here in the Watershed Explorer. Under Optimization Trials, we're going to basically be creating a new record right here. So without further ado, New, and I'll just call this Test Opt 1, and then Next. Now I need to select the basin model. I only have one basin model, so I'll go ahead and click Next. At any time, I can go back or click Cancel or the X button in the top right to go back or to exit. This is the third and final step. I select the meteorologic model. I'm just going to go ahead and select this first one here and click Finish. Right now I have a Test Opt 1 optimization trial that's been added here, as well as over in the Watershed Explorer. Now I have options to copy, rename, delete, and edit the optimization trial that I just created. So quite simply, you just select whatever trial you want and then click the button. So if I want to click copy, I just copy the data, give it a new name, and then click copy. Rename is pretty self-explanatory. Again, just give it a different name, delete, and then edit. If I click edit, it's actually going to bring up the components editor, which will allow me to edit not only the description here in this top row, but a number of other parameters, which we'll be seeing in just a little bit. All right, so I'm going to close that. Over here in the Watershed Explorer, I mentioned in the Compute tab, we have this optimization trial. If I click that, I can right-click, copy, rename, and delete that way as well. You're also seeing options to compute, which will be not in this lesson, and then add parameter, which we will talk about, but later on. If I click on this option, now I see my components that are associated or the parameters associated with that optimization trial. Down here in the optimization trial components editor, I've got a main tab here for optimization trial, and then I have other tabs here for search and objective. In the optimization trial tab, I have my description, my output DSS file, which is the project directory slash and then the name of the trial.dss, which is really the same format that's being used for simulation runs. So as a rule of thumb, I'm going to make sure that all of my optimization trials are unique, not only within optimization trials, but also within simulation runs. After that, it's my output. So I can output the data, either all, minimal, or selected. And then after that, I've got the basin model and the meteorologic model. These are the two selections that we made in steps 2 and 3 when creating the trial. So we can go ahead and change those right here if we want. After that, we have the date time. This is the date, start, and time that we want that optimization trial to run for. Unlike the simulation runs, the optimization trial doesn't have an associated control specification. So this is where we would define the start and end date time of the optimization, which will capture the output results at this specified time interval. All right, the next tab over is our search tab. And we have our search method right here. The default is simplex, but there's two other options, univariate and differential evolution. HMS has two ways to run optimization in order for the model results to match or most nearly match that observed data. The first is the deterministic method. HMS adjusts parameter estimates so that the simulated results match the observed data as closely as possible. There are two deterministic methods, which is the simplex and the univariate method, which I'll talk about. Optimal results provide the same single set of optimal parameter values each time using these deterministic methods. The other method type is stochastic. HMS has two stochastic methods. I'm only seeing one here because the other one is currently hidden, but that one is a differential evolution is the one that we can use. In the stochastic method, HMS produces a collection of equally probable parameter sets based on the distribution of the parameter population. Parameters are treated with uncertainty and must use an uncertainty analysis. And it does not return a single set of optimized parameters, but rather a different parameter set with each trial. So let's start with univariate. This is one of the deterministic ones. With univariate, we only have one variable, or sorry, one parameter, one decision variable that the optimization trial can use. And if you try to add a second parameter, it won't let you. All right, the next one is simplex. This is the other deterministic method. And simplex is based on a gradient search technique, and it requires two or more variables. So if you have more than two, go ahead and use simplex. The last one is differential evolution. This is our stochastic method we can use. In this search method, parameter values are varied randomly using crossover and mutation, which is seems kind of similar to the genetic algorithms, but it's a little bit of a simpler method. And then the last method that we're not seeing is Monte Carlo Markov chains. So I won't talk any more about that, but the user's manual does talk about this other stochastic method. Once the method is selected, you'll notice that the different parameters below change up. So in the case of univariate, all we need to provide is the max number of iterations and the tolerance. Max number of iterations is just like it sounds. It's the maximum number of iterations that the compute will run. So if convergence hasn't already taken place by this 100th iteration, then it will terminate based on the max iterations. Of course, we can change this number to something else, but 100 is the default that it starts us with. Tolerance right here is basically a stopping criteria for once convergence has been found. 0.01 is the default value. If I select simplex method, we still have max iterations and tolerance, but now we have this tolerance criterion and the options are absolute or relative. In the case of absolute, convergence is assessed based on the absolute tolerance or the absolute difference between the nodes of the simplex. The criterion is more sensitive to the actual objective function values, which may vary greatly based on the objective function type that we select in the next tab over here. In the case of relative tolerance, right here, convergence is assessed based on the relative tolerance or relative difference between individual nodes of the simplex. This criterion is less sensitive to the actual objective function values. The last method, differential evolutions or DE, we still have max iterations and tolerance, but now we have min iterations. This is the minimum number of iterations that the compute needs to run until convergence is even assessed. Then we have a population size and a seed size. So these last three parameters are only for differential evolution. Population size refers to the number of sets of parameters that are used in the optimization. 30 is the default value. It may be too many or too few. If it's too few, then the optimization may have trouble converging. And if it's too many, it simply may take too long to run. So this is like may require some trial and error to figure out a good population size. And then the seed value here is a random number that the user provides HMS to seed the randomization, since computers can't create purely random numbers by themselves. The next tab over is objective. And our options here for the first drop down is our goal. Either it's minimization or maximization. The user's manual mentions that objective functions measure the variation between the computed model outputs and the target data, which is the observed data. I sometimes switch those two terms around, observed data and target data, because the model is aiming to match that observed data. The optimization routine runs until the objective function value is sufficiently optimal or the maximum number of iterations is reached, or some other stopping criteria. A sufficiently optimal result means that the computed model output has a sufficiently good goodness of fit score when compared to the target data or the observed data. Oftentimes, a streamflow, hydrograph, or model element is used to compare with the model output. So for instance, on my map here, the basin model map, I have an output or a sink at the downstream location of the watershed. And in this particular model, I do have an observed streamflow hydrograph, which is associated with this sink element. And then that's going to be compared with the hydrograph of the model output. And then by modifying the parameters, hopefully that output from the model can closely match the observed data hydrograph. So in the case of a hydrograph and using a sink as my selected element or location, then the model element used for comparison must have an observed hydrograph for the time period over which the objective function must be evaluated. All right, so let's just hop into the description of some of these parameters here. Minimize and maximize deals with the actual value in the time series field here. So if I want to minimize the discharge, that's an option, or I can maximize the discharge. As you notice, when I change the goal, I have different parameters that showed up down below. The user's manual is on screen now, and I just brought this over to show the different minimization goal objective functions and their motivation. So this table here is for minimization, and you're seeing the different options here and then a description. So for instance, we have first lag autocorrelation, mean of absolute residuals, mean of squared residuals, and so on. If I move that back and then I select the minimization, I'm sorry, and then the statistic right here, these are the different options that I was referring to. So I didn't mention that earlier. We have mean of absolute residuals, root mean squared error, and so on. Peak weighted RMSE. These are the different ways to calculate that deviation or the variation between the model output at the selected location and the observed data that is provided by the user. If I go ahead and select maximize, there's also a table in the user's manual for maximize goal objective functions. The next field down is location, and this is the location in the basin model map that we are using for comparison. This is the location that we need to have our discharge data for, in this case, an observed hydrograph for us to use for comparison. The time series here shows the discharge and precipitation. These are our two options. These choices are dependent on the location itself. So East Branch Mahoney Creek is actually a subbasin, but if I select a junction or an outlet, for instance, I should only have discharge right here. The next field down is statistic, and what I have for my options when I have discharge selected is discharge volume and peak discharge. This is the parameter that we want to maximize. So maximization right here refers to discharge volume or peak discharge. If my model, for instance, had a reservoir in it and I selected a reservoir for the location, for the time series, I would have pool elevation, and then for the statistic, I would have peak elevation. The last parameter here is data transformation. The three options are no transform, Box-Cox transform, and log base 10 transform. The purpose of applying a transform is to improve the model's performance by addressing issues like nonlinearity or skewness. So no transform just means no transform is applied. The log base 10 transform simply takes the log base 10 of the values, and this is a little bit of a simpler approach, but a more flexible approach is Box-Cox, and that transforms the data into normal distribution or a shape that transforms normality. This is a little bit more flexible, but could take a little bit longer. Both of these transformation methods require positive values, so a shift may be applied if necessary. Next, it's time to add some parameters to our optimization trial. This first optimization trial that was created before we started has some parameters already, parameters 1 and 2. And now to add a parameter, we just go ahead and right click, add parameter. So there's parameter one. Based on my search method, I have differential evolution. Let's select simplex, or actually let's select univariate and then try to add another parameter, and it's not going to let me. Okay, so that checks out. If I go simplex, then I should be able to add another parameter. So I have parameters one and two. Certain parameters are well-known data points, easily measured and not used for model calibration. These are things such as the subbasin area and the reach length. And these are parameters that we're not going to be able to change in the optimization trials. Other parameters may be estimated, but not known exactly. And this is the type of parameters that we will be able to use in our optimization trials. For instance, hydraulic conductivity is loosely based on some soil properties, but not known exactly. And we can only measure soil properties at so many locations anyway. The third type of parameter can only be estimated by comparing computed results to target results, which HMS refers to as observed data. So an example of this would be something like snow water equivalent. All right, let's go ahead and select parameter one. And then first what we need to do is select the element. Our options are all subbasin, precipitation parameters, and then all of the hydrologic elements that are upstream of our selected location. So right now our selected location is this sink, which is the outlet to the watershed. So all of the elements upstream of that should be selected here, at least subbasins and reaches, not junctions. But if I change the location to maybe like Stump Creek Subbasin, then I'm only going to see Stump Creek Subbasin and then these first two options here. So let me go ahead and do that real quick. I'm going to change the location to Stump Creek and then back to parameter one. And my locations have now changed to only show Stump Creek and then, of course, all subbasins and precipitation parameters. I'm going to go ahead and change that back though. There's the outlet and parameter one. Okay, so let's go ahead and talk about these. I'm going to describe these in reverse order, starting with the individual hydrologic elements. So for instance, if I select Stump Creek, then my options for parameters are the parameter data that's associated with that subbasin or that hydrologic element, which include parameters that are associated with the loss method, the base flow method, which is deficit and constant and linear reservoir respectively, as well as Mott-Clark, that's the transform method, and then simple canopy is the canopy method. So if you remember what I just said, and then I select on Stump Creek, and then the main subbasin tab has those methods that I just described. Deficit and constant is the loss method, transform, Mott-Clark for the transform method, simple canopy, and linear reservoir. So if we look at the loss method, deficit and constant, for instance, and then I select loss right here, I see four parameters. There's the initial deficit, maximum deficit, the constant rate of infiltration, and then percent impervious. Now, percent impervious is not going to show up as one of our parameters because it falls into that first category of a parameter that's easily measured and can't be used for parameterization in optimization trials, but these first three can. So initial deficit, maximum deficit, constant rate of infiltration. Keep those in mind. I'm going to go back to the compute tab in the Watershed Explorer, click on parameter one, and then I have Stump Creek selected already. And here our first three none records. Our options here is deficit and constant rate, initial, and maximum. So this is initial, maximum, and then the infiltration rate. So if I go ahead and select that, now I have the initial value logged and then maximum and minimum range. So this is the infiltration rate parameter for the Stump Creek subbasin. It's starting off at 0.05 because that's what it was initialized in the subbasin data itself. And I'll just go ahead with that. We also have a locked value and minimum and maximum. If locked is changed to yes, this basically tells HMS that the parameter value should not change during the simulation. The default is no because most likely you're going to want it to change. And then the maximum and minimum values here are usually way more extreme than necessary. I believe it's the actual maximum values allowed. So whatever it is, go ahead and change it. Increase the minimum value to something more reasonable and decrease the maximum value to something more reasonable as well. The smaller the range of values here, the smaller the solution space for the optimization. The user's manual also mentions that the minimum and maximum set here are not hard constraints, but rather if the algorithm exceeds the minimum or maximum values, a certain penalty is applied, which leads me to believe if a trial run results in a parameter being at the minimum or maximum value, or perhaps a little bit beyond, it may be worth revisiting this range and extending either the minimum or maximum in whichever direction that the optimal value was up against, the min or the max. What I just said about this initial value locked min and max, that's true for all the parameters that we select, but I still want to go back and describe some of these other options. That was the example for subbasins, Stump Creek, but Mahoney Creek right here is a reach. So if I select that, now we have different parameters that are associated with the reach, specifically the routing. So if I select that Mahoney Creek in my basin model, then I have Muskingum as my routing method. K, N, and X are the three parameters that I can select. So if I select, say, the number of subreaches, N, the default is 5, and then it can change between 1 and 100. I'll go ahead and change those ranges to something more reasonable. But let's go back to the basin model. I'm going to click the Components Manager, and then Basin Model, Mahoney Creek. Here is the routing method for Mahoney Creek Reach. And if I select the Routing tab, here is that default value of uh, N is 5. It's right down here. So the default value for K is 5. The default value for X is 0.25. Okay, let's go back to our parameter data right here. The user's manual provides tables that describe what parameters are available for which different hydrologic elements. So in the case of a subbasin, the different canopy methods are listed here: dynamic, gridded simple, and simple. And then the parameters that can be used for optimization are in this parameter column. So this is just one table right here. Let's scroll down. This next one here is for subbasin, but the surface method. So we have gridded simple, simple, and dynamic. The next one down is loss method. This is what we were looking at. We have a curve number, deficit. Deficit and constant was the one that we were looking at here. So we have initial deficit, maximum, and then the constant rate here. So let me just scroll down to show you more tables. Again, the link to this website will be in the description of the video. There's the transform method for subbasin, base flow methods. After that, we've got reach. So there's the lag, and then snowmelt parameters that's associated with the basin as well. Okay, so that was the different hydrologic elements. We also have subbasin right here. So if our parameter applies to the entire subbasin, we now have a number of different parameters, which includes scale factors. Special parameters called scale factors have been included that adjust all similar parameters upstream of the evaluation location together in the same direction. So if you select a scale factor, you go ahead and scale that where 1 is the default value, and then you can scale it using a minimum and a maximum value, which are a multiple of the original values. The last element to describe is precipitation parameters. So my choices here refer to the precipitation method selected for the selected meteorologic model. So when we created our optimization trial, we have a meteorologic model for this one happens to be September 2018 observed. Let me go to the components menu. Look here. I have a gridded precipitation method. So let me go back to that parameter for my options are coordinates X and coordinates Y. But if I selected a different precipitation method, I'd have different parameters right here. So again, if I select X, I'd have an initial value, and then I would have to say yes or no to locked, probably no. And then, yeah, these are some extreme values for minimum and maximum. We'd have to make those much closer to our initial value. The user's manual mentions a few recommendations. First of all, when creating parameters, don't create the same parameter twice. Also, try to avoid adding two related parameters. Also, too many parameters can be detrimental due to the cursive dimensionality, and the order of the parameters does matter. For instance, if you're getting results that don't quite make sense, maybe try changing the order of those parameters. Some of the final thoughts on this topic are setting up the parameters and search data and the objectives is an iterative process. Determining the optimal parameter values is not an automatic process that takes the modeler some trial and error to figure out, because you're going to be modifying the number of iterations, the search tolerance, and also the ranges for each parameter. But once you get all that set up, you'll be ready to go, have your optimization trial saved and ready to compute.